Okay, let's try this new method and see if it works. All right, I want to make that bigger. Okay, all right, so now we're moving on to video number 2, and it's all about projections. All right, so you can see here, I'm on the second page of my 2.5 document, and you can see the picture that I put here around the projection. So the idea about a projection is that it is basically the shadow cast of one vector onto another vector. So you can see that vector A, which is at an angle of theta degrees from vector B, B is lying horizontally, vector A casts its shadow onto vector B. And it's essentially the horizontal component of vector A. I've indicated it in red. And if you were to identify the magnitude of that vector, it would be just by using our cosine law, it would be the magnitude of A cos theta. So that's the magnitude. And the direction in this case is the same direction as B. That's because this angle theta is an acute angle. So it's casting a shadow down on top of angle B. If it was an obtuse angle, you could see the shadow it would be casting would be on negative B. So the opposite direction, but still along that same horizontal. Okay, so it is a vector solution. Okay, whenever you do the projection, it will be a vector solution, okay, with a magnitude and a direction. The direction will either be the same as vector B that it's being cast down onto, or the opposite if it's an obtuse angle, okay? So please make sure you understand that idea. So the dot product itself, which is this application, is a scalar, but the result of the projection is a vector, okay? And you can see here, it is a vector projection of A onto B. And so you can think about it, A is the big letter here, and it's projecting itself down onto B. So in this case, just be very careful when you're reading this. Is it A onto B or B onto A? Well, it's A, because it's the big letter, onto B, which is the little letter, okay? So I'm going to very quickly go over how these formula were derived, but you don't have to worry about this. I'm just explaining it so you have a bit of context. Okay, so if you look at, this is the vector projection, meaning it's got a magnitude and it has a direction, okay? So this first part right here, this is a scalar. I have my dot product divided by the square of my magnitude of B, my bottom vector, okay? And what I did when I shifted from here to here, I just wrote out my formula, my geometric formula for the dot product, which is A, B cos theta, and then I broke up the square from here. So magnitude of B times the magnitude of B, okay? If you think about this, this can just cancel out. So essentially what you're doing is you're finding this as a fraction. You're basically taking this projection, the length of that projection, which is, as I mentioned, A cos B, excuse me, A cos theta, and you're taking it, that's the numerator, over the length of B. Okay, so it's kind of like a scalar fraction, and then you are multiplying it by B. Okay, so this is giving you a scalar multiple of B in relation to that projection magnitude. Okay, don't have to worry about this. I'm just telling you where this comes from. Okay, and then the scalar projection is just literally the length of that projection with relation to vector B. Okay, so here I have the dot product over the magnitude squared of B times vector B. Here I have the dot product just over B, the magnitude of B. All right, I've written it out again. You can see those cross out, and I'm left with the magnitude of A cos theta, which is just this same thing. Okay, so those are the formula that I'm going to use. Notice here I've used the geometric formula for the dot product, but you can obviously use the algebraic formula. And that's when we don't know the theta between the angles, but we have the position vectors for A and B. Okay, so keep these formula on hand. You do not have to memorize them, okay, but you do have to read them and know how to use them. All right, so moving on to this page, okay, I'm going to pause my video because I want you to find the projection of U on V. Read this very carefully. So U onto V. So when I do my formula, okay, I'm going to have the dot product of U, V, okay, and then I'm going to have the magnitude of V squared, and I'm going to multiply that by the magnitude of V, all right? When it's little like this as the part of the projection statement, it's going to be the same vector that is on the bottom and that is multiplied as a direction vector, okay? So please calculate this. Your answer will be a vector, okay? Which means it will be an ordered triplet, or no, in this case, an ordered pair, excuse me. And then we're going to do a drawing over here. So you can try the drawing as well. Notice what I've done, because I want it to be clear. I've actually doubled the scale. So when I draw this, I'm going to have -1, +4 up here. I'm going to use 2 squares for each one, okay? So I'm going to pause the video. I'm going to come back. I'm going to have solved for the projection, and I'm going to have plotted my two vectors U and V, and then we will look at this together. Okay, so please pause.